Okay, so now we are up to our next to last lesson on determining series, convergence, or divergence. And so this lesson is based on AP topic 10.6, and I'll show you where we're at on the roadmap in a second, but basically what we're saying is if everything else fails, and we still cannot determine convergence or divergence, then you use these last two tests. We're going to learn something called the direct comparison test, and then the limit comparison test. So where are we in our grand scheme of things? So if you know a series is not geometric or p-series, if you know it's not alternating, which we haven't learned yet, that will be our next video, then we go through all of these green boxes to try to figure out convergence. We start with the nth term test. If it doesn't equal 0, it diverges and we stop, but if it does equal 0, we have to go on to another test. We try the ratio test, but the ratio test can also be inconclusive. If the limit as n goes to infinity, the ratio test equals 1. So then you would go try the integral test, and the integral test sometimes is just difficult or impossible to use. And so finally, if all else fails and you've run out of ideas, we go to what are called our comparison tests. We're going to learn these two in this video, the direct comparison test and the limit comparison test. And these are last resorts just because they're just usually a little bit more abstract and maybe a little more difficult. Now honestly, after you practice them a few times, you might really like them. And so you can make your own judgment. But let's go ahead and learn the first of the two, called a direct comparison test. And I suppose we should just think about what the word comparison means for a moment. So we are going to compare our series to another series that we already know, that we can easily figure something out about. Now if we go back up to our roadmap, there are two main series that we can easily figure something out about. Geometric series, we can just figure out what the ratio is, the common ratio, and where the n is, and we were able to figure out convergence or divergence pretty easily. And a p-series, if we have 1 over n to a power or 1/nth to the power, we can figure out what that power is and easily figure out convergence or divergence. So on these comparison tests, what we're really going to be doing is we're going to be taking a more complicated looking function that we are taking the series of, and we're going to try to compare it to a geometric series or p-series. And we have a couple rules for that. So here we go. First is the direct comparison test. And the direct comparison test is a way to compare your complicated series to another series that you can already determine, kind of like what I just said. And so here's the deal. You're going to take your series, a sub n, and then we're going to take another series like a geometric series or p-series. And actually your series can also be the b sub n. It can be the bigger of the two. But we need to be able to write the two series in some kind of way that we definitely know one series is bigger than the other as we are plugging in numbers for n. And we'll see an example in a minute. Now there are only two ways. Once you compare those series, there are only two ways that this direct comparison test works. Basically, if the bigger series, the b sub n, converges, okay, then a sub n also converges. And well, think about what that means for a second. The bigger series already comes in on a number. Okay, so the b sub n is the greater one, where we have a statement here that shows which one's smaller, which one's bigger. And so if your bigger series is all pointing towards a number, say 4, then the series that's smaller than it can't point to infinity. It can't like break past the bigger series. Now, just because the bigger series might point to 4 doesn't mean the smaller series also points to 4. Remember, we're not trying to answer what it converges to. We're just trying to answer if it converges or not. So we'll say it again. The first of the two ways is that if the bigger series converges, then your smaller one will also converge. Okay, now it works the opposite way as well. If your smaller series diverges, then the bigger one also has to diverge. And you can kind of visualize this as well. If your smaller series goes to infinity, Well, your bigger series can't come to some limit, some number. It doesn't make any sense. The smaller series has busted through to infinity. It's diverged. So the bigger one will diverge as well. So that's the basic idea of a direct comparison test. Now, number 3, it's up to you to find a function of which you know the convergence or divergence that is either smaller or bigger than your function so you can compare them. And number 4, in perhaps every case, and I will say yes in every case, we will compare our function to a geometric series or a p-series. So let me give you an example of this. So here we go. Let's suppose that our series is goes from 1 to infinity of 1 over 2 plus 3 to the nth power. So by itself, that by itself is not a geometric or p-series. Maybe we could use the ratio test to figure this out. But I want to teach you how to use the direct comparison test whenever nothing else works. So here we go. I recognize that our series, we'll call this A sub n. It looks kind of like it could be a geometric series. And the idea is that I see that it has some number to an nth power. So I'm going to say it kind of looks like 1 over 3 to the nth power, which of course we could rewrite 1/3 to the nth power. So it kind of looks like that geometric series. So let's compare these two series. Well, and so we're going to call that one Bn and ours was An. Well, A sub n is always going to be smaller than B sub n for all values starting at n equals 1 and above. Now, how do I know that? Because my series has an extra number added in the denominator. And anytime you divide by a number in the denominator that's bigger than another number, the bigger denominator is always the smaller number, right? 1/5 is smaller than 1/3. So as soon as we add that 2 to our 3 to the nth power in the denominator, that makes this one smaller than without adding the 2 to it. So what does that mean? That means that my series is always smaller than the geometric series B sub n. Well, what do we know about this geometric series? Let's figure this out. So my R is 1/3, and you need to be memorizing and keep on working on that roadmap and memorizing your series. We know that if our R, the absolute value of our R is between 0 and 1, then it converges. So that means our B sub n converges. Well, okay, we only have 2 ways that the direct comparison works. And one of the ways here in part A said that if our bigger series converges, then our smaller one also has to converge. And that's what we have here. The bigger of these two is 1 over 3 to the n, and it's geometric and it converges. So that means that A sub n must converge as well. So we will say our series from 1 to infinity of 1 over 2 plus 3 to the n converges by the direct comparison test, and that is, I'll just put a comma, comparing it to the geometric series 1 over 3 to the nth. So that's how the direct comparison test works. Find a geometric or p-series that looks very similar, such that you can easily tell that one is always going to be greater or less than the other. Now they can also be equal. I mean, if you can find a series that's exactly equal to yours, then that's easy. Just find the convergence or divergence of that equal series and yours will be the same, but that's pretty rare. Now, the problems that we're going to have with this is that sometimes we will do something like what we did, and we'll find out that our bigger series diverges. Let's just imagine that this problem diverged. Well, that just means a sub n is inconclusive, right? If the bigger one diverges, that doesn't mean the smaller one diverges. It could go to a limit, it could diverge, we don't know. It's underneath. So the tricky part is to really keep straight in your head letters A and B here. That if the bigger one converges, your smaller one converges. If the smaller one diverges, your bigger one diverges. But other than that, we can't say those backwards. So just got to be really careful there. Okay, well, finally there's one more test that you can use that is probably last for a reason. It can be maybe tricky, or maybe it's just one we just don't practice enough. Maybe if we practiced it a lot, it wouldn't be tricky. But there's a lot to do in AP Calculus BC, so maybe we can't practice everything a lot. And so this is a pretty rare test. We don't use it a whole lot. But it is called the limit comparison test for convergence. And it's kind of like our last resort. Let's read. The limit comparison test is useful if you cannot specifically determine if your series is always bigger or smaller than a geometric series or p-series. See, on this direct comparison test we did, we were able to tell 1 over 2 plus 3n is always smaller than 1 over 3 to the nth. That's always going to be the case. But you know, maybe there would be extra stuff in our function in the denominator that doesn't quite match up so nicely with 1 over 3 to the nth power, and we just can't tell. Well, that's where this series comes in. So how do you do it? Well, you're going to take your series, and then you're going to take a geometric or p-series, we'll call it Bn. Now, it doesn't have to be an exact copy of yours. However, it's super useful if it has the same degree and it is similar, right? You want it to look similar. Because what you're going to do is if you take the limit as n goes to infinity of your series divided by the geometric or p-series that you're using, and if you get an answer for that limit that's finite, so no infinity signs, and positive, so not 0 and not negative. So if you get a finite limit answer of your series divided by that known series, so that limit exists, then that means that your series and the known series will both do the same convergence or divergence. It's really a kind of a cool tool. And you know, if you had more time to process and to kind of dive into this, it's such a really neat idea that the limit of your series and a known series, if the limit is a positive finite number, then your series and the known series will have the same convergence or divergence. But now listen, please get this. Whenever we find that limit number, L, that's not the convergence number, okay? That doesn't mean that we converge. Up to this point, still, the only series we can find the convergence number for is a geometric series. But that doesn't mean that we converge to L. L is just the limit number of. Okay, so what does that all mean? Well, this means that if the limit does exist, then you can use your geometric and p-series test to determine if your actual series converges or diverges. So let's look at an example of this one, and that will pretty much get us through this test, this set of tests, comparison tests. Okay, so let's imagine we have a series, n equals 1 to infinity, and let's see, we're just going to make it a quadratic in the denominator, a little more complicated, probably with that minus 4n in there. It's not always going to be less than 1 over 3n squared, so we can't use a direct comparison test. So I am going to do a limit comparison. Boy, if I could write neater, then you might be able to read what I write. So let's do a limit comparison test. Now we're going to call that a sub n. Let's compare it to, now we want to pick a geometric or p-series that just closely matches ours. So 1 over 3n squared, because we can think of that as 1/3 1 over n squared, or 1/3 1 over n squared. So now we see that that's a p-series. Our p is greater than 1, and so we know that this converges. Well, okay, that's great, but we haven't proven that we have a finite limit, so we can't just automatically say our series converges, right? Just because we found something that looks like it. So here's what we need to do. The limit comparison test, the limit as n goes to infinity, and look at it up here again. It is our series divided by, well, our function divided by the similar function. So we saw this with the ratio test. We're going to be dividing fractions. So the easiest way is to say our function, and then instead of dividing by the other one, we'll say multiply by the reciprocal of the other one. So you just kind of get used to doing it that way. So we want the limit as n approaches infinity of this product. And look what we have. Since we chose the same power, then we can go ahead and say that the limit equals the coefficients of those powers, 3 over 3, which is 1. So my limit is 1, and let's kind of go through a couple of quick checks here. That is finite, yes. And right, look at what we need to do. Finite and positive, and so it is positive. So since the limit of our function divided by that known function is a finite positive answer, and since that function converges, then our function converges by the limit comparison test. Now, notice that we got a limit of 1. That number 1 doesn't mean anything really. I mean, it's not what we converge to, so don't try to think that. That's not what we're answering here. It's just, since it's a finite positive number, it means we're allowed to take on the convergence or divergence of the other function we were comparing to. Okay, one more thing to read. It really shouldn't be too difficult. It really shouldn't be difficult to find an appropriate series to compare your series to in either one of these, limit comparison or direct comparison. If your series has any version of 1 over n to a power, use a p-series. If your series has any version of a number to the nth power, use a geometric series. Okay, big picture, and we're done with this video. So, big picture. We're working through all of these steps whenever we don't have a geometric series, p-series, or alternating series. Maybe divergence from, or maybe the nth term test is inconclusive, the ratio test is inconclusive, the integral test is maybe too difficult or impossible, so now we go to our comparison tests. And look, by the time you get here, anything in AP Calculus, you should be able to, one of these tests should be able to tell you convergence or divergence. There's only one more type of series to look at. It's called an alternating series. It kind of does its own thing, and that'll be the next video.